Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 6, Integration and Accumulation of Change. Today's topic is 6.7, which is the fundamental theorem of calculus and definite integrals. Enjoy today's notes. All right, welcome to 6.7 on definite integrals, and we're going to talk about the second part of the fundamental theorem of calculus in this video. In our last video in 6.6, we talked about properties of definite integrals, and we sort of gave a preview that we were going to be able to take integrals by hand. And so 6.7 here is going to be the first sort of way that we're going to start learning about how to take integrals by hand without a calculator, which is going to be nice because we can do this with equations without needing a graph and needing to find that area under the curve. So we're going to start off with this definition, and there's this word that's called an antiderivative. So we spent a bunch of chapters talking about these things that are called derivatives, and now we have this word which is an antiderivative. So an antiderivative of a function f of x is a function capital F of x. So we notice the regular function is f of x. The antiderivative we label by using this capital F of x, and we say that capital F of x has a derivative which is f of x. So we talked about this maybe briefly in another video, but we know that for the regular function, this little f of x, if we take the derivative of it, right, if we take the derivative, we get f prime. And if we take the derivative of that, we get f double prime. And if we take the derivative of that, we get f triple prime. And you could keep going as many ways as you want. However, the question then is, what do we have that when we take the derivative of that gives us f of x? And this antiderivative sort of answers that question. We have this capital F of x. If you take the derivative of it, is little f of x. So if we were going in the opposite direction, to go from little f of x to capital F of x, we are taking the antiderivative, or it's actually called antidifferentiation, just like taking the derivative is differentiation. So, for example, let f of x be equal to 3x squared. We know that the derivative of f of x is 6x, right, by that power rule. So we can say that 3x squared is the antiderivative of 6x. 6x is the derivative of 3x squared, but if we take the antiderivative of 6x, we end up with 3x squared, because 3x squared is going to be the antiderivative of 6x, and that is since if we take the derivative of 3x squared, we get 6x here. And so the derivative of 3x squared is equal to 6x. When we take an integral, though, it is actually taking the antiderivative of a function. We've talked about like taking integrals here, graphically, right? Finding the area between the curve and the x-axis, but actually it's doing this thing, it's finding an antiderivative of the function, which is super cool. The area under the curve is represented by an antiderivative. They're actually the same thing. The area under the curve is the same thing as this antiderivative, which is sort of mind-blowing. It's super cool. So what we're going to do today is we're going to be looking at how do we find antiderivatives? How do we do this? And we're going to first start by looking at the power rule for finding a derivative. So this is way back when in chapter 2, chapter 3, the power rule for finding a derivative, probably chapter 2 is probably one of the first rules for finding the derivatives that we know. And the power rule, if you remember, this is the rule that says if you have x cubed, that if you take the derivative of that's going to give you 3x squared, right? So the derivative of x cubed is 3x squared. And what do we do here? Well, we notice that whatever the exponent is, we bring that to the front as a coefficient. We multiply that with any numbers that are already there, and then we subtract one from the x-axis, or subtract one from the exponent. So here in this case, if our exponent is n, that n comes to the front, it multiplies by our function x, and then we subtract 1 from the exponent. So the derivative, using the power rule, of x to the n is n times x to the n minus 1. Step 1 is we multiplied by the old exponent. Step 2 is we subtracted 1 from the exponent. And so that's how we would use the power rule back in the day, back when we learned chapter 2, when we were first introducing derivatives. Now, antiderivatives, it's the reverse order. It's essentially they're essentially inverses of each other, and so we're gonna swap steps. and do the opposite of them. So in this case, for step 1 of the antiderivative, we're going to do the opposite of what step 2 is. Instead of subtracting 1 from the exponent, we're going to add 1 to the exponent first. And then after that, we can go the opposite. So then this is multiplied by the old exponent. So we're going to divide by the old exponent. Except in this case, we're going to divide by the new exponent. So what does this mean for this function here? So if we have x to the n, first we need to add 1 to the exponent. So that's going to become x to the n plus 1. And then we need to divide by whatever that new exponent is. So we're going to divide by n plus 1. So this is essentially our power rule for integrals, for antiderivatives. And just like the power rule for derivatives, this is like one of the most important rules for finding an antiderivative. It is so important. I would like highlight this. This is huge. It is the equivalent of the power rule, which we did for derivatives, except it's for integrals and for finding definite integrals for this. So let's take a look. We're going to find the antiderivative capital F of x. All right. So finding the antiderivative, we need to add 1 to the exponent. So this is going to become, we're going to call this capital F of x, because that's the antiderivative. And we're going to add 1 to the exponent, so that's 3. And then we divide by the new exponent, which is 3. So that is going to be our antiderivative of x squared. Now again, let's talk about what this means. We're saying that this function, now if you take the derivative of this, you'll get x squared. Is that actually true? So if I was trying to take the derivative of x cubed over 3, is that true? Well, by the regular power rule, I would bring that 3 down, so it's 3 x squared, and then that 3's there, those 3's would cancel, so that's just x squared here. So amazingly enough, yeah, we did actually find a function here that was able to, if we took the derivative of it, gave us x squared. So we found the antiderivative. Now, let's ask a question here, which I'm going to sort of step back here. How would this derivative be different if I added on, say, like 6? What would happen? Well, if I took the derivative of the 6 would go away, right? And we would still have x squared. What happens if this was plus 1,000? Well, since this is a constant, if I took the derivative of that, we would still have x squared. Okay, well, what if we subtracted a constant? What if this was like minus 3.14? 159265535. What if we had like a decimal approximation of pi? Well, this is a constant, and if we took the derivative of it, we'd still have x squared. So what we notice here, interestingly enough, when we take the antiderivative, if we have a constant on it, that we're going to still end up with the same derivative in the end. And so because of that, the constant doesn't matter whether it's positive or negative, big or small. To represent that it could be really any constant, when we take an antiderivative, we add this thing that has a plus c on our equation. And sort of this is an important thing for me to just sort of like highlight when taking an antiderivative. When taking an antiderivative, always add a plus c. And again, that plus c is representing, we could have any constant here, and that would still be part of the antiderivative. But if we took the derivative to get back to x squared, the derivative of that constant would go away. So we could have a plus 6. We could have a plus 1,000,000 here. We could have a plus whatever, or minus whatever here, as long as it's just a constant, and it would still be an antiderivative. So interestingly enough, there are like actually an infinite amount of antiderivatives here, one for any value of like c that you can think of, right? All the decimals, all the values you can think of. So cool. So we just represent that as a plus c to say, hey, we could have any value here that we want. All right, let's take a look at number 2. We've got lowercase f of x is equal to 5x cubed plus 6x 6 divided by x cubed minus 1. First off, like the regular power rule, I'm going to rewrite this so that there's no denominators. Let's rewrite this. We've got lower case f of x is equal to 5x cubed plus 6x to the negative 3 minus 1. And so the reason for that is now I could apply the power rule or this like antiderivative power rule in order to do this problem. So what do we call that? We're going to call this capital F of x. The 5 here is going to stay the same, and we're going to add 1 to this 3, so that becomes a 4. We divide by the 4. Then we've got plus 6. We need to add 1 to negative 3. Negative 3 plus 1 is negative 2. And we're going to divide by that new exponent of negative 2. And then this was a constant. When we take the antiderivative of that, that's going to be a minus 1x for that. So if we want to simplify, capital F of x is going to be equal to, looks like 5 over 4, x to the 4th, minus 3. And then that x to the negative 2 is going to go to the denominator, so over x squared, and then minus x here. So this would be our antiderivative of the function f of x here. And we can always check to make sure that we got the correct answer by just taking the derivative of this function and doing that. And of course, I forgot the one thing that I said to always do. We need to add a plus c. So let's get rid of this box. I'm going to put a big old plus c here on the end because we need to have that when we take the antiderivative to represent the fact that we could have any constant here and it would still, when we take the derivative, go back to this. All right, number 3. Slightly running out of room here, so let's get a little bit closer. I'm going to rewrite this just like we said for the previous ones, and I'm going to move this over here. So this is going to be equal to x to the 1/2 power plus 3x to the negative 1/2 power. Moving that square root up to the numerator makes it negative, and then x to the 1/2 is the same thing as the square root. Now if we apply our power rule, capital F of x is going to equal to x to the 1/2 plus 1. So 1/2 plus 1 is 3 over 2. And we need to divide by that 3 over 2, plus 3 times x to the negative 1/2 plus 1. So that's going to be positive 1/2. And I'm dividing by that 1/2 down here. And so if we want to simplify, we've got that. Don't forget your plus c. So that's going to equal, we're dividing by a fraction. So that's the same thing as multiplying by its reciprocal. So that's going to be 2x to the 3 over 2 over 3. Notice there 3 over 2, the fraction flipped because we multiplied by the reciprocal here. And I'm going to multiply by the reciprocal here because we're dividing by a fraction again. So that's going to be 3 times 2 over 1. So that's going to be 6x to the 1/2 plus the c. So altogether, that looks like 2/3 x to the 3 over 2 plus 6 root x plus c. It's going to be our answer for problem number 3. Nice. All right. What about some special integrals? Well, we talked about the power rule. This is obviously useful for any functions that are polynomial functions, right? Like these are pretty basic, no weird trig functions or anything like that, no exponential logarithmic functions, but we've got some rules here that we should talk about. Before we get to the integrals, I want to remind you how the derivatives of sine and cosine work. So we know that if we have sine of x, that if you take the derivative of it, you get cosine of x. And if you take the derivative of that, you get negative sine of x. And if you take the derivative of that, you get negative cosine of x. And if you take the derivative of that, you go back to sine of x again. We can go around and around and around as many times as we want. You could take the 20th derivative and you could just keep going, figure out what the next one's going to be. Okay, first derivative, second, third, fourth, fifth, as many as you need, going around loop-de-loop. Super nice. So if we know that an integral is the antiderivative, we can actually just go the opposite way around this circle. So instead of going clockwise around this circle, we go counterclockwise around this circle. If I want to find the antiderivative of sine, well, that's going to go the opposite direction. That's going to go to negative cosine. So that's going to equal negative cosine of x. And because we took an antiderivative, it's going to have a plus c there. Similarly, if I have cosine of x and I want to take the antiderivative of that, starting at cosine, I'm going to go the opposite direction. That's going to take us to positive sine of x plus c. So we can actually use this sort of same framework that we were thinking about derivatives earlier in the year, back in chapter 2, chapter 3, to do antiderivatives. You know, the antiderivative of negative cosine, hey, that's negative sine. If I want the antiderivative of negative sine, hey, that's positive cosine. And you can use that to help you keep track of the derivatives and the antiderivatives for sine and cosine. That is super, super nice. We're going to get now into the fundamental theorem of calculus. We said that there were two parts to this. We've talked about the first part already earlier this chapter 6. Great. So the fundamental theorem of calculus, the second part, if f is continuous on the interval from a to b, then the area under the curve of f from a to b can be represented by this, right? We know from earlier this year that this integral symbol represents that area under the curve of f between f and the x-axis. But we can actually do this with antiderivatives, and here's what it says. It's going to be equal to the antiderivative of the function with the upper limit of integration, our b, plugged in, minus the antiderivative with our lower limit of integration, a, plugged in. So interestingly enough, I can find the area to do this, but also I could represent this using antiderivatives. So sometimes I might be trying to evaluate a integral by looking at the area under a curve, but if they don't give me a graph, I can use equations to do this as well, and that's f of b minus f of a. Whoa. Interestingly enough, there's no c's here, and I'll just mention that why is there no c? Why is there no constant? Because when I take the antiderivative here, this is technically f of b plus c minus the antiderivative at a, so f of a minus plus c. And then what happens here is we end up distributing this negative sign, so this ends up being a minus c, and then the c's cancel each other out. And so we don't need to actually worry about it. So an interesting effect of this is when evaluating definite integrals, no need for c. There's no need for the plus c. That's when you're evaluating definite integrals, because in this case, because we're doing f of b minus f of a, essentially those c's cancel out and you're left with just f of b minus f of a. So that's cool. That's nice. Let's see it in some problems here. Number 4, evaluate the definite integral. Use a calculator to check your answer. So number 4, what do we need to do? Well, we look up here at the fundamental theorem of calculus. If I want to evaluate this integral, looks like I need to take the antiderivative and then plug in my limits of integration and subtract. So that's the goal. Let's start with that antiderivative first. So the antiderivative of 4 is going to be 4x, and then the antiderivative of negative 6x is going to be what? Minus 6x squared over 2. And the way, so mathematicians, we essentially, want to write, have some sort of notation here to think about, okay, I have taken an antiderivative, but I haven't plugged in these limits of integration yet. So for me, the way that I write this is I'm going to put this in brackets to represent that I've taken the antiderivative. So I have now taken the antiderivative, but I haven't plugged in my limits of integration yet. So I'm going to leave those limits of integration here on the outside of this bracket. I put the upper limit 5 here and the lower limit negative 2 here. This is a signal to me and to the reader that I've already done the antiderivative parts, but I haven't plugged anything in yet. And so once I plug those in, then I'm not going to be doing these brackets anymore. Depending upon, for those of you who are looking, with my class or maybe looking at notation from different books, there are a couple of different ways that people write this. Sometimes they just draw a line here with those two numbers. Sometimes they do parentheses with those two numbers. This is my preferred way of doing it. Cool. So what do we need to do? Well, in this case, we see that the b is what we plug in first, that upper limit of integration. We subtract, and then we plug in our lower limit of integration. So this is going to be well, actually, first I'm going to simplify, because why not? We got 4x minus 3x squared. We got the 5, we got the negative 2. I still have not plugged in my limits of integration, so they're still there. Now, we're going to plug in. So 4 times the 5 minus 3 times 5 squared. So we've plugged in the b. We've plugged in this upper limit of integration first. We now need to subtract, because that's what our rule here says, is we need to subtract those two things. We need to now subtract our lower limit of integration. So 4 times negative 2 minus 3 times negative 2 quantity squared. Whoops, and that's not on the outside. And that's our lower limit of integration. So we essentially plugged in the 5 first to both of the x's. We then plugged in the negative 2 to both of the x's here. And then, of course, we're subtracting between the two of those. Notice now, I don't have the brackets anymore. And I don't have the limits of integration written anywhere anymore, because I've plugged them in already. So this is sort of a placeholder here, these brackets of saying, hey, I've taken an antiderivative, but I still need to plug in these limits of integration. All right, so let's simplify. 4 times 5 is 20. We've got 3 times 25, so that's minus 75. We've then got a minus negative 8, and then looks like a minus 12 here. So that's going to be equal to, negative 55 minus a negative 20. So negative 55 plus 20 is going to be equal to negative 35. That is what this integral is going to be equal to. So the integral from negative 2 to 5 of 4 minus 6x dx is equal to negative 35. And this is how I would evaluate this by hand. And this is how I would show the work for this on, for example, a no calculator section of the AP exam, or a no calculator section of a quiz or a test for this. Now, our instructions here say to use a calculator to check your answer. So let's do that. We're going to switch over to our calculator and just check to make sure that the actual integral is the same. I encourage you to use your calculator to check your answers as you're going through these. That's a great way and a great tool to be able to do that. So let's do that. Okay, so again, we're checking our answer using the calculator. In our previous video, we talked about this, but let's review again. So to take an integral in a TID3, TID4 with math print, we hit the math button, we go to number 9, which is fn int, and this brings up our sort of format here to plug in each of these squares. We're going to need to put something in. Our lower limit of integration is negative 2. Be careful when plugging these in that you're using a negative sign and not the subtraction sign. The calculator does not have those interchangeable, so be careful, right? Your negative is down there. And then you're going up to 5, and then the equation that we're looking at looks like 4 minus 6x, and our variable is an x here. Now, we just evaluated this by hand. We saw that it was negative 35. What do we get here if we do it in the calculator? Negative 35. So the calculator is a great tool for us to check our answers and make sure that it's correct. I encourage you to do that as you're working through these. Again, we should know how to do this on both the calculator section and the no calculator section. You want to make sure that you're getting practice in both of those. Let's go back and try number 5. All right, so continuing on with problem number 5, let's evaluate this definite integral here by hand. So for problem number 5, we need to take the antiderivative here first. So what we're going to do is we're going to say that, let's rewrite this so that we can apply our power rule. So this is the integral from 1 to 4 of x to the 1/2 power minus 1x, or just x to the negative 2 dx. Now this has been rewritten. We can apply our power rule to find the antiderivative of this polynomial function. So I'm going to do my bracket. We've got x to the 3 over 2 divided by 3 over 2. So we added 1 to our exponent. That gave us 3 over 2. And then we divided by that new exponent. And then that's minus x to the negative 2 plus 1 is negative 1 divided by that new exponent of negative 1. And then our limits of integration are 4 and 1. I'm going to simplify this before we plug in those limits of integration. So this is going to be equal to, since we're dividing this fraction, dividing by a fraction, we're going to multiply by its reciprocal. That is going to give us 2x to the 3 over 2 divided by 3. And then we've got a minus, so that becomes a plus. and then that x is in the denominator, so 1 over x from 4 to 1 here. And then so from there, we know we need to plug in our limits of integration. This is really as simplified as we can get. My goal here is to try to do this by hand. Again, afterwards we could use our calculator to check those answers. But let's plug in the 4 first. So that is going to be 2 times 4 raised to the 3 over 2 power, all divided by 3, plus 1 over 4, minus, we're going to now plug in the 1, 2 times 1 to the 3 over 2 divided by 3, plus 1 over 1. Again, what did we do? We took our upper limit of integration, we plugged that in first, we then subtracted, and then did our lower limit of integration second for that. Notice my brackets now went away because I've plugged both of those in, and I don't need to bother writing the brackets with those limits of integration there anymore. From here, we just need to simplify. How do we evaluate 4 to the 3 over 2 power without a calculator? In this case, we know that to the 1/2 power is the square root. So 4 to the 1/2 is going to give us 2. And then 2 to the 3rd is 2 times 2 times 2. That's 8. So 2 times 8 is going to give us 16 over the 3 plus 1/4 minus, well, 1 to any power is going to be 1. So that's going to be 2 times 1, which is 2 over the 3 plus 1 over 1, which is 1 here. Let's keep simplifying here. So now, if we're going to be able to combine these, we're going to probably want a common denominator. My goal here, again, is to do this without a calculator. So here I'm going to multiply both of these by 4. We'll multiply by 4 here. So that's going to be 16 times the 4. 16 times 4 is going to give us 64. So that's going to be 64 over 12 plus, here I'm going to multiply both of these by 3. So that's going to be 3 over 12. Now they both have the same denominator. That's great. Then we've got minus. Here I'm going to need to multiply by 4. So I have a denominator of 12 as well. So that's going to be 8 over 12. And then I'll make this one a 12 over 12. So plus 12 over 12. So 64 plus 3 is 67, minus 8 is 59, and then we've got a minus another 12, so that's going to be, what, 47? So this is going to be equal to 47 over 12 for that definite integral. And of course, I'd encourage you to go check on your calculator, go plug that in, make sure you're getting the same thing. What it's probably going to do is going to give you a decimal approximation. And then if you look at the decimal approximation and you compare that to the decimal approximation of 47 over 12, it's going to be the same answer, except this will be exact, which is super nice. Cool. Let's try number 6. Number 6, we're taking the integral from 0 to pi over 2 of 4 sine of x dx. First off, hey, let's use some of those properties we learned last lesson. We know that this 4 is a constant, and it's just multiplying the sign. So let's bring the 4 outside. This is 4 times the integral from 0 to pi over 2 of sine of x dx. We know that the antiderivative of sine of x is going to be negative cosine of x. And that's going from pi over 2 to 0. And so we took our antiderivative. It's in the brackets now. Now we need to do our fundamental theorem of calculus. We're going to plug in our pi over 2. We're going to subtract. We're going to plug in 0. So this is going to be 4 times negative cosine of pi over 2 minus negative cosine of 0. And if we think about our unit circle, pi over 2 is going to be kind of a cosine of 0. So that's 4 times essentially negative 0 minus the cosine of 0 is 1. So minus negative 1, that's going to be a plus 1 here. So negative 0 plus 1 is 1 times 4 is going to give us 4 as our answer for problem number 6. Nice. Cool. What about problem number 7? Well, in this case, they're giving us f prime. If f prime of x is equal to x squared minus 2 and f of 1 is equal to negative 2, then what's f of 3? So in this case, an interesting thing here that we can think about. Notice the x values that we're talking about, f of 1 and f of 3. Well, we have the derivative here, and what we can think about with the fundamental theorem of calculus is that if we take the integral from 1 to 3, if we take the integral from 1 to 3 of our f prime of x dx, that's going to equal the antiderivative of f prime, which is f, just regular f, of 3 minus f of 1. This is by our fundamental theorem of calculus. Here, because we had the f prime, we know the antiderivative of that is just regular f. That's why I don't have capitals here. But if we're trying to find f of 3, right, we're trying to find out what f of 3 is, that's what this is right here, we can actually just add f of 1 to the other side. So f of 3 is equal to whatever f of 1 is plus the integral from 1 to 3 of f prime of x dx. So this is what I'm working with. So I'm just highlighting this because this is the goal, what we're working with here. So if I want to find out what f of 3 is, we know that f of 1 is -2, and then we need the integral, we need the antiderivative of this this function, right? We've got a visual of f prime here, great, but if I'm going to actually find out what that is, I'm going to need to plug in the x squared minus 2 and need to actually find that antiderivative. So in this case, I'll actually do some side work over here. If we're trying to evaluate the integral from 1 to 3 of x squared minus 2 dx, let's do it. So we take the antiderivative first. That looks like that's going to be x cubed over 3. Then we've got a minus 2x. We then need to plug in our limits of integration. So that is 3 cubed over 3 minus 2 times 3 minus our 1/3 over 3 minus 2 times 1. Again, what did I do? I plugged in my upper limit of integration to the antiderivative first. I then subtracted, and then I plugged in my lower limit of integration second. 3 cubes 27 divided by 3 is going to give us 9 minus 6 minus 1/3 minus 2. So that looks like that's going to be 3. So we've got then 3 minus, what's that? So negative 5 over 3. So negative 5 over 3 is plus 5 over 3. Nope. Yeah, that is gonna be plus 5 over 3. So plus 5 over 3. And so then that's going to be, what, 14 over 3? All right, so if we've got that, we know that this integral here is going to give us 14 over 3. And so that's going to be, I'll just plug that in all the way over here. 14 over 3. That is what this integral just became, is 14 over 3 from our side work here. And then if we subtract 2, so -2 plus 14 over 3, that's going to be equal to 8 over 3 or 2 2/3. Either one of those would be acceptable answers for this, but that's going to be our final answer here. This is my side work, which is worth having here on the side just to show how I did that antiderivative. But that's going to be it. Super sort of cool here that I can actually find values. So I had f of 1 and I had f prime. Even though I didn't have the original function f of x, I was able to use the fundamental theorem of calculus to find that actual value by doing this process. Super nice. All right, so in this, we learned how to find an antiderivative using our power rule, which is essentially the reverse of our power rule for derivatives. You've got some practice problems. Our solutions are posted. Try out that mastery check and come to class with any questions that you've got. Have a great rest of your day.